Hey, everyone rolling in. Thanks for joining us today. We're going to start in just a few seconds as folks trickle in. All right, we'll get rolling this morning. Thank you to everyone for joining us in the webinar today. We're going to be discussing hourly tracking for U.S. energy storage systems. We have a great panel here and a number of experts who are excited to talk with you about this exciting opportunity. From a high level, storage is a firming technology for variable clean energy and does not always receive credit from status quo clean energy markets for this particular valuable process. As you'll hear today, tracking clean electricity through storage as it time shifts the value of those clean electrons can offer a new revenue stream and market opportunity that does not exist today, as long as it is done with integrity and accuracy. This is a critical next frontier in modernizing clean energy markets. Today, you'll hear from a few experts. Miles Evans from EPRI will share an overview on the state of storage technology and markets in the US. Arin Kaye from EPRI will discuss how storage can be incorporated into tracking systems. Killian Daly from EnergyTag will explain what the EnergyTag standard offers in terms of tracking granular certificates through storage assets. And Alec Miller from Quinbrook will share how they have demonstrated the EnergyTag standard in the real world. This webinar will be 1 hour with 10 minutes for Q&A reserved at the end. So please use the Q&A function to type any questions you have throughout the presentation, and we'll get to as many of those as we can at the end. The webinar will be recorded and we'll share it around afterwards. So with that, I will turn it over to Miles with EPRI to do his presentation.
Thank you very much. And can you see my presentation?
Yes, we can.
Very good. Yeah, thank you. Hello, everyone. My name is Miles Evans. I lead the Planning and Economic Analysis Research Area in the Energy Storage Program at the Electric Power Research Institute. And today I'm going to spend just a few minutes talking about how energy storage is used in the United States today, the scale of its deployment, and things like trends driving duration for these energy storage systems. And I'll close by posing maybe a couple of questions about how the pretty complicated multi-use applications seen for energy storage compare with a energy and emissions tracking system. All right. So we're going to start out quite general here. And most of these slides are going to be plots like this that express the quantity and duration and other attributes of energy storage in the United States. The data that we're looking at comes from the EIA, in particular Form 860, which asks all the large generators in the United States, and in this case, storage systems in the United States, to answer a number of questions about their system, how it's being used, et cetera, so that they can do this tracking effort. What this data will include at the end includes some residential, community, commercial, industrial type customer energy storage systems. But in the first part of this presentation, we're going to focus on the large utility scale energy storage systems and how they're used and deployed. So by way of a very brief introduction to energy storage in the United States, here is a plot showing every large storage system that the EIA tracks. We see a lot of storage systems clustered around the pretty small end of the spectrum. Toward the left is small power capacity, and toward the bottom is small energy capacity on this plot. However, we are seeing bigger and bigger systems all the time. So we will be seeing more of these this plot be filled out in the future. I drew a line here at the 4-hour duration mark, which means that the usable energy capacity of the storage system, or rather, sorry, the nameplate energy capacity of the storage system in this case, is able to support the full power capacity discharge for 4 hours. We see some systems a little bit longer, but most are either exactly 4 hours or less still today. Diving into these duration trends a little bit more, we're going to explore this by geographic detail as well. But this histogram plot, well, almost a histogram, it's weighted by the nameplate power capacity of the storage systems, can express that indeed most of the systems in the United States operating today have a duration around about 4 hours, or at least that is the most common duration. 1 to 2 hour duration storage systems are also fairly common, and we'll explore where and why in a moment. But a lot of the resource adequacy and market rules and energy shifting needs have been pushing systems to that 4-hour duration in the past, though of course 8 hours or more do exist in battery form, even in lithium ion battery form, even in the United States as well. Most of these systems, and I don't have a chart to show this, are lithium ion batteries. I've excluded pumped storage hydropower resources from these images and conventional hydropower and everything else like that. But there are a few flywheels and a couple of other small systems of different technologies represented. The trend in the average duration of these storage systems is upward over time, though, as you can see in recent years, the average duration has leveled out around 3 hours, which is the average. As we saw in the previous chart, we have a bunch of 4-hour systems and a bunch of 1 to 2 hour systems, and they average out to about 3 hours for these large operating battery energy storage systems that we're looking at. This chart shows the capacity weighted, so the power capacity weighted average duration deployed in each year. So if a system became operational in 2015, that's the only year that system will impact the data for, or the results for, in this plot. So it is a little bit noisy, but there is a clear upward trend. And we are seeing in proceedings around the country increasing demands for resource adequacy accreditation for energy storage, meaning that they're requiring longer durations to achieve equivalence with a conventional generator. And that sort of thing. There are also, as the power system continues to evolve, changing needs for energy shifting and balancing to ensure reliable operation as well. So an increasing trend in duration over time. But this is not geographically consistent. So I'm showing here the 4 states, Arizona, California, Nevada, and Texas, with the most nameplate power capacity of energy storage in the United States right now. This is not weighted by the load size in each of these states. This is just the absolute megawatts of storage capacity. So some states may actually have quite a bit higher representation of energy storage in their system, but these are the ones with the most systems or the most power capacity. And looking at this, we can see on the right, I should also say the y-axis here is duration, and this is a density plot on the vertical axis. So the wider these shapes are, the more represented that particular duration is. And so if we look on the right, we can see that Texas here represents 1 hour duration storage very strongly in its fleet, whereas these other Western states, Arizona, California, Nevada, the most common duration is 4 hours. And this is in part driven by the markets and the needs. Systems in Texas might be doing a lot more of the faster balancing applications, whereas systems in these other states may be doing more energy shifting, renewables integration, hybrid system applications, I mean, and get a fair chunk for some of them anyway of their value from providing resource adequacy and offsetting the need for other resources there. Though that's not always the case. So different places with different needs are driving different durations of storage. And in general, the trend in duration is going to be upward. And now we'll get into a little bit of how these systems, these large energy storage systems, are being used. So part of this EIA survey collected information on the applications that these energy storage systems are meant to perform. So this isn't a representation of how much they're performing each of these applications, and nor is this application list an exhaustive set of market products or non-market applications that storage systems can do. And some of them are broader categories even than that. But this is the framework in which they collect pretty exhaustively this data about energy storage systems in the US. So that's what we're expressing here. What we can see by looking at this data is that these large systems are on average providing 2.7 of these applications each. So some will do 2, some will do 3, et cetera, and it averages out to about 2.7. So these energy storage systems are not doing one thing alone. They're not just shifting energy in time when charging when the price is low and discharging when the price is high, or the cost of generating electricity, depending on where you are. Many of them, in fact, most of them, almost all of them, are doing other things as well. Most represented here is frequency regulation. So, following an automated generator control signal, which changes on a 4-second to 4-second basis to make sure that inflows and outflows of power in any given region balance and the frequency stays relatively constant. So there are well over 10 gigawatts of storage systems operating in the US today who are labeled for use in this frequency regulation application. That's quite a lot, and frequency regulation plays in an interesting way with some other services here that I'll pose some questions about. In particular, to set this up, about 3.2 gigawatts of storage operating today are labeled both to be able to absorb excess renewable generation and provide frequency regulation. So we have these systems and quite a significant power capacity representation here, where storage systems are both charging from green electricity quite a bit, but also fluctuating their power output on a very fast basis to balance the frequency on the grid. And that might pose some complications or challenges when doing the tracking. And so the question I'll leave open, and I don't think we'll resolve anything today, but is just be thinking about how these sub-hourly and very quick power and energy transfers should be handled in an energy and emissions tracking system. And in particular, what I'm talking about here is represented in the plots on the right here. If I'm participating in a market region, I might be scheduled to discharge, but if I'm providing regulation, frequency regulation, then I might be called upon to actually charge for parts of that hour, discharge for other parts, et cetera, to balance the frequency on the grid. And tracking these energy transfers is a real challenge even for outside of this emissions context. The other segment I'll close with here is the customer energy storage systems. These represent quite a bit less power capacity and energy capacity than the utility scale systems today, but are still a substantial amount of storage. Most of these are doing some form of backup power, especially in the residential category, and also they can be operated to reduce the bills, especially for the commercial and industrial category through demand charge management, et cetera. Or they can participate in demand response programs and other ways of generating value there. But the use case is fairly different than the utility systems, and the representation is substantially smaller on the whole, but still significant. I will pause there and pass it to my colleague, Arin.
Thank you, Miles. And I noticed that we just did a smooth transition there without Alec, so apologies, we're used to working together. As Miles said, I'm Arin Kaye. I am the research lead for greenhouse gas emissions accounting and strategic applications here at EPRI. And what I'm going to talk about today is incorporating storage into certificate tracking markets. And before I do that, what I wanted to do was provide a little context, recognizing that we have a diversity of demographics on the line to tracking systems. So this graphic I pulled from the Center for Resource Solutions report here, linked. And a tracking system is an electronic database with basic information for each megawatt hour of renewable power generated on the grid. So the visualization here on the right of the screen will walk you through how that megawatt hour would show up within a tracking system. So it will get generated. In our example, it is wind generation, and then it will get uncoupled the electricity, which is the 1 megawatt hour of electricity from, in this case, the renewable energy certificate. And that certificate will then be the thing that gets transacted in the system. So oftentimes the megawatt hour of electricity gets put into the general grid power, and that can either be called null power or some other term depending on where you are. These certificate transaction systems are online databases, and they track using specific identification numbers that are assigned to each megawatt hour. And to give you an idea for those located in the United States of some tracking systems, this map, and I recognize that the state labels or provincial labels are basically illegible, but the point is to illustrate that there is not one standard tracking system or registry within North America. However, there are credible regional tracking systems throughout North America, and you will see, I believe, all of them illustrated here in various colors. There is not, again, this makes it challenging for standardization, but it does make it very interesting to think about how a renewable energy certificate would then be bought or sold within this market. And then what types of generations being tracked? The key point that I want to illustrate on this slide is that there are first two different clumps. There is the all generation tracking systems. So that is renewable, which also includes large hydro and nuclear, and they will also track fossil fuels. The most common that we talk about, though, are renewable energy certificates, and those track renewables only, which can either include or exclude hydro, which is kind of complicated. But the note I want to make here is that storage is not included. So as Miles talked about, there are many different services for storage. And within these renewable tracking systems, they currently don't incorporate it. So then as we think about this concept of where we are currently within tracking systems, we have an opportunity to integrate storage for a key use case that Miles had on his slide, where in his visual, over 10,000 megawatts are used to time shift. And I want to use the use case here on time shifting to really exemplify the benefit that tracking storage can have on our certificate system. So what you'll see in the visual on the left is a graphic from an AES white paper on 24/7 carbon-free energy from 2021. The green is the renewable energy output. In this case, it is solar. And the blue is the load curve. So what you'll notice is solar produces its electricity in the middle of the day. And what we're missing are the two wings of your bell curve. So where storage can be particularly useful is to fill in those sides by time shifting the electricity generated in the solar production. I know that that's a little complicated and it's challenging to track. And so then we're going to get into what some of the challenges are here. And I wanted to leave you all with a series of questions on food for thought. So from my perspective as an emissions accountant, our biggest challenge is accurate accounting. And so my three questions here are some big picture, some really granular. If we are incorporating a battery system in and trying to track its emissions intensity, and it's getting charged with grid mix, how do we calculate the emissions intensity? How do we assess the state of charge and then the discharge and the various allocation methods that are used to do that? And would we have to drain the battery in full in order to be able to account for the emissions of discharge power if it is then later charged, say, from 50 to 100% with solely renewables? So there's some key complications here in terms of understanding the emissions intensity of battery storage as we incorporate it into these markets, assuming that it is not co-located with some kind of intermittent renewable generation. Think of those as solar or wind. And then my last question to pose to the group as we think about tracking systems is, how do battery losses get accounted for? Assuming that something like 5% of the charged electricity is lost during storage, what is the emissions intensity of that lost power? And how would we incorporate that into the emissions of our discharge power? With that, this is me, this is my contact information, and I am going to give it to Alex to queue up our next speaker.
Thanks, Arin. And I don't mind the smooth handoff between Miles and Arin. That was nice. But I will do the next transition over to Killian, who will explain and talk through the EnergyTag standards and sort of offer some answers or some thoughts on the questions Arin posed up. And as a reminder to everybody as well, please put questions into the Q&A function, and then we will moderate a Q&A after the presentations. All right, over to Killian.
Great. Thank you so much, Alex, and to the folks at EPRI as well for teeing this all up. So what I'm going to do is just run through the EnergyTag standard, and before I do that, just give a couple of perspectives from our point of view, at least about how clean energy markets can be improved. I think they're great questions that have been posed, and we've been kind of working on answering some of them and testing some of them in the real world, which Alec will come to in a bit. But of course, this is an iterative process. This is probably the newest and definitely the most important part, I think, of updating clean energy and attribute markets. So it's good that we have these conversations together. One graph I just wanted to show, and this is something you see right across the world with a lot of solar penetration. So this is the hourly percentage CFE in CAISO in 2023. Not surprisingly, plenty of sun during the day there, but obviously some hours then when there's very low carbon-free energy availability. And so we need to more and more, and we see this across the world, right? We need to get that clean electricity from day to nighttime. That's one of the challenges of the transition. And I think this graphic kind of shows this well. We need to these storage devices to fill in those gray points on this graphic. Obviously, the issue is today that if you're doing annual or monthly or anything above hourly accounting, you can basically use the solar RECs at night without having to store them. So there's no need for storage to get to a 100% renewable target. And that's becoming more and more of a problem. So obviously, hourly accounting is more accurate. It develops a proper price signal for the availability of carbon-free energy. So in theory, following basic economics, it should be cheaper to buy CFE when it's very sunny and a bit more expensive when there's not so much CFE on the grid in these gray hours. And obviously, this should send an additional price signal for storage above the power market price signal to actually move these clean attributes from day to night time and sell these granular certificates or hourly RECs at a premium in those hours of clean energy scarcity. Another thing, not to get too technical, but this is something when I talk to folks in the storage industry and both here in Europe and across the world, one thing I hear, especially in the more advanced markets, the UK, maybe California, traditional revenue streams such as ancillary services, those markets are getting more saturated over time. And so pure market arbitrage will become more and more important. And what this graphic on the left is showing, it's a piece of research out of Imperial College London looking at various regions around the world. But actually a lot of this price arbitrage happens, you know, in a relatively small number of hours. About a quarter of the year is when you'll get most of the market value, up to 90% of the market value out of price arbitrage. So basically what this means is, you know, more revenue streams are going to be important. And we see these granular certificates and also 24/7 PPA, so like longer term PPA contracts that are integrating storage that are firmed. So whether that be 80, 90 or 100% firmed PPA contracts, they could be useful additional revenue streams for revenue stacking for storage operators. So just to talk about the EnergyTag standard, about how we do this tracking, because it's quite novel. So we released the second version of our standard earlier on this year with a lot of input. We ran many working groups on this with practitioners, academics, and experts, and registries, of course, to discuss, well, how can we do this tracking? How can we set a framework for doing this tracking? And obviously, as a principle, to go out and test this, as we'll see in a bit, and then further improve this over time. So basically the process is, you can check out our standard below, and we'll provide a link also after in the notes. There's a 3-step process by which we do this tracking. We charge the battery or the storage device at a certain time, and then you can retire hourly certificates matched in time to those charging records, we call them. And obviously you can only retire as many hourly recs as physical power has been charged into the battery in that given hour. Then you store those attributes in a reservoir, you account for losses, which I'll get to in a bit, and then you discharge that energy again, and you can issue storage discharge granular certificates, or, you know, basically storage discharge hourly recs in other language. And obviously that can also only be limited to the actual discharge of the storage device in that hour. And it's super important that this hourly correlation between charging and clean energy production and discharge and creation of those discharge granular certificates is maintained. That's a very important principle. Finally, and very importantly, we need an allocation methodology for basically describing how the gray energy from the grid and the clean energy from the certificates, how that gets allocated from charging to discharge. And there's different rules and ways of doing that that we need to think about and evaluate. On losses, so basically losses have to be accounted for, otherwise it's not a credible scheme. What we've come up with is basically that should be based on measured data, so real data from the storage device, ideally at an hourly interval, and Alec will get to this in a second, I think, but it could be over a longer period as well, but it needs to be based on measured data rather than being based on defaults for the whole operating period of the battery. Defaults could be used for 6 months, but probably not much longer than that. Measured data is very important given how much circumstances change across different storage device types and of course things like climate variables, etc. When we're considering losses, we have kind of detailed calculations about this in the standard if people want to go through them, but charging losses, discharge losses, self-discharge losses, and basically looking at the state of charge of the storage device are all crucial variables when we are evaluating this efficiency factor for losses. And on allocation, basically we need this credible way to allocate charge to discharge attributes to make sure it's both physically representative and also feasible. There's 4 options we have kind of come up with. There's FIFO, first in, first out. Weighted average, which is like taking a blend of all your attributes in the reservoir at the time of discharge and allocating that to discharge in proportion. You could have a target green percentage. So, you know, every hour you try to get out 90% green. And if you have those attributes, you can do it. And then there's what we've left open, the storage operator decides to leave that flexible and open for the storage operator. Again, these must balance accuracy and feasibility, and much more detail, including equations, are given in the standards to kind of how you might implement these various approaches. Just to give a visual example, here's an example of FIFO. So we think about using the train analogy, and that kind of lets us see how the charge blend of green and gray attributes gets transferred through to discharge. And this is really a first in, first out scenario. First in, you're first back out. Then you might have a storage operator decides, and this leaves more flexibility, of course, to optimize revenues from the sale of granular certificates, for example. So, if the electricity and attribute prices is much more expensive, for example, between 7 and 8 p.m. Than between 8 and 9 p.m., then the operator could just allocate all of the attributes to that hour and choose to not discharge any green and discharge only gray between 8 and 9. Obviously, this comes with certain questions, I would say, around the physical representativeness of that. Because as you know, and as you see on charging, there's a certain blend of attributes in each hour, and that blend looks very different for the hours on discharge. So while that may be more flexible, it also does raise questions around accuracy. So we kind of have to think through all of these things as we standardize. So that's the overall framework. There's worked examples in our standards. We try to strike this balance between complexity and simplicity. And I think very, very important. We need more testing, as always with these things. So if folks want to have real operating assets and go and test this stuff, definitely reach out to us both for more information and also to potentially run a kind of a pilot. So I'm going to leave it there and pass it back to Alex to introduce the next speaker. Thank you so much.
Killian. I'll turn it over now to Alec Miller with Quinbrook.
Great. So thanks everybody for the excellent introduction to the concepts we're facing here and sort of the opportunity to really use batteries more to help with the energy transition, in particular the time shift element of batteries, the capability that it gives us. I'm going to talk today around a few areas and add some context to Killian's introduction. I'm going to talk in particular about how we tested the EnergyTag standard and approach on a battery in ERCOT. What was that case study? What did we find? How did it work? And add some context to sort of some of the key results we had. So first, just a quick introduction. Quinbrook is a value-add infrastructure investment manager with a specialist focus on the energy transformation. We work across low carbon and renewable energy supply, energy storage, decarbonization. I'm with Private Energy Partners, which is an affiliate of Quinbrook, and we provide the Quinbrook Group with enhanced capabilities in digital tools, in asset management, and revenue optimization. So let me jump in a bit to the overview of the case study and then key results and sort of things we learned. But first, just to add a few other points to sort of why, what are the benefits of doing hourly tracking on batteries. And the first one, actually, I'll talk and show some results later on the fact that you can more accurately measure the carbon footprint of batteries. And this is, before we talk about creating discharge certificates, it turns out that, if you're using an average method for calculating your scope 2 of your batteries or your impact, your avoided carbon effect, if you're averaging it out, you're basically sort of flattening the load profile of the battery. So if you do it with, using the hourly profile, you get a much more accurate result. And I'll show some of those in a later slide. The second point is that you can prove where your discharge slices came from. And, think if you're using a battery, particularly for green industrial applications like green hydrogen under 45V in the US or European standards, you need to be very accurate about showing, where did you get the discharge from a battery if you're using that to time shift renewable energy to support an electrolyzer or any other sort of green industrial application. And then lastly, as Killian mentioned, under the EnergyTag approach, you'll be able to create new discharge certificates that have the source of the charge with the timestamp of the discharge on a battery. And so really a proven method that you can create those new certificates for batteries. And as Arin mentioned, that's something that's being updated, with the registries because batteries are not currently there. So that's up and coming as part of the updates that registries are doing. So what was the case study? So we implemented this on a 50 megawatt 1 hour battery in ERCOT. There's two summaries of this that you can see. One is in Canary Media with the link down below, which has sort of a higher level summary the more detailed summaries at quintrace.com/hourly case study. Quintrace is the software platform that we developed to track, hourly charges and discharges, and including measuring batteries. So you see it there, those two summaries, if you want to see a high level or more detailed. And so we worked on 3 basic challenges of implementing the EnergyTag standard at the time, and we were working as part of the EnergyTag working group, implementing methods on loss calculations, realizing that, as Killian mentioned, sort of the average annual calculations don't work. State of charge data is not always reliable on an hourly level. And then when you have a mix of grid and renewables in a battery, that's more of a challenge than having a homogeneous battery, either all grid or all renewables. So those are some of the things we were focused on as we worked through this case study. We took the real charge-discharge profile cycle of the battery, and then we simulated a solar input because we weren't changing that for the case study. So we simulated about a 10 megawatt size solar input. So some of the charges were solar and some came from the grid, for which we used the data for ERCOT. Killian already talked through sort of the general approach here, so I'll just introduce it high level again and then talk more on the allocation methods. So as Killian mentioned, we charge the battery, we keep track of those slices of energy by type and by quantity, by amount. We put those into the reservoir. We calculate the losses per hour. So those are done, based on each hour's calculation. So very, near real-time calculations of those. And then we discharge those slices using a particular allocation method. I put up a graphic to add to what Killian said. FIFO Killian covered, which works really well for a homogeneous battery. So if you're not worried about, what's going to come out next, you can run, FIFO is a well-known accounting standard, so you can run that very effectively and keep track of the slices by when they went in. The one on the bottom was the one that we worked on with when you have a battery that has a mix of renewables and energy that has carbon associated with it, typically from the grid. Then you want to keep track of those in a different way. And in particular, it was important to know that a certain percentage of your renewables were going to come out each hour, for example. So you can set a target percentage, 90% or 75%, and the application will try to satisfy that percentage, and then fill in the rest with the energy slices that have carbon associated with them. So this gives you a much more conscious way of knowing each hour I'm going to try to hit my percentage. And so therefore, if you're matching to an electrolyzer or to a certificate market, you know what's going to come out in that hour. So how well did this work? So this is an example that's written up in more detail in the case study. Here on the left, we've got solar on the top left area going into the battery. So we have 2 charges from December 5th of different quantities that came from the solar. And on the bottom, we have a charge from November 25th that also went into the battery. So those were inside the battery reservoir, where we keep track of those slices. So you can see we have the yellow colors, which are the solar slices, the gray, which is the grid slice coming with carbon intensity associated with it. And then those were actually discharged jointly using those allocation methods on December 18th. So, it came out as part of a group of discharge that was 170 kilowatt hours. And so we were able to keep track of inside of that discharge. These are the slices. Those slices came out along with some others on December 18th. And so here we used the target green percentage to do that, and ran through all the calculations for state of charge, for losses, etc., and are able to prove that, hey, those came through the battery at these times. We applied the losses and they've come out. So it worked really well for A, keeping track of slices, and B, proving the time shifting in that battery. So inside of the Quintrace application, which I mentioned, this is our battery inspector, where we look at a battery at an hourly level, right? So we look at, on the left, the charges, on the right, the discharges for the hour. And here we can keep track of, again, what are the percentage of grid, what are the percentage of renewables that go in for each hour, each time period. And doing that, we can measure avoided carbon in scope 2. And we did a comparison, in this case, of those 2 attributes to a monthly average method. And this was for a site that had both solar and batteries on the site. And we saw that avoided carbon, we saw an improvement in accuracy of up to 16% and scope 2 up to 37%. And the reason is that, if you take that monthly average for solar and battery, right, you're just assuming that its profile is flat, that it did the same thing every hour of the day, which is not true. So we say this is a lot more accurate. To do it hourly, you're much, much closer to the actual profile, operating profile of a generator and a battery. So really good improvements in accuracy, much closer to the physical reality of those assets. So there's lots of good areas to work on. And Miles and Arin mentioned a few of these, as did Killian. So these are some of the areas that we're highlighting to work on in 2025. Killian's going to talk about, and Alex, about some ways that you can participate if you'd like to. Testing on a greater range of batteries with different duty cycles and service cycles. Standardizing procedures around the batteries. How do you set them up? How do you configure them? How do you deal with data losses, right? Anomalies that occur. And lastly, simplifying ways to validate the battery outputs for registries. Right? Registries are used to validating generation mostly. And generation is pretty straightforward, right? You can compare it to the similar time period, say a year ago. When you're doing it A, hourly, and B, on a battery, it's more complex. So that's one of the things we want to work on sort of going forward. So yeah, there's a lot more detail in the case study on the website, and happy to answer any questions.
Amazing. Thank you, Alec. And thank you to all the presenters. We have plenty of time now for Q&A and have questions rolling in. So feel free to keep dropping those in there. And then panelists too, if there's any questions in there you'd like to just type an answer to, feel free to do that as well. So first question for Killian, if you could just briefly elaborate on how you were describing granular certificates contributing to revenue stacking, and in particular storage assets using and tracking granular certificates to contribute to revenue.
Yeah, sure. Well, I think basically the fundamental concept is that, today rec markets don't give any price differentiation depending on when that energy was produced. So there's essentially a flat signal across the year. And so there's no signal to shift in time because the signal is flat. So the idea is that obviously if you have hourly granular certificates, you can really tell when exactly that energy was produced or released from storage. And let's say at nighttime, as I kind of went through earlier, at nighttime in California, for example, where there's very low availability of CFE on the grid, and there's demand from a 24/7 customer, from a hydrogen electrolyzer, for example, that wants to be compliant with regulations, then that storage device discharging should be able to pick up a premium because of the scarcity of GC availability at that time. Aurora have done some modeling on this in Europe. I'm not exactly sure what numbers I can share there, but I'll try to find some public information to share in the follow-up notes as well to give some idea of the orders of magnitude here of potential spreads. But that's the basic concept here, that obviously moving to an hourly price signal should benefit storage because of its ability to time shift.
Thank you. Next one, I'll throw this one out for everybody. This question is, how can a utility customer partnership make storage work for 24/7 or hourly matching when an RTO or an ISO has the control to optimize the storage for market operations? Typically, this is from the question, typically the energy will be cheap overnight when the load is low and expensive during the day when load is high. And this might be the opposite of what a customer might want for their particular matching purposes. So curious for thoughts from anyone on that.
I'll just say it's a very good point. And energy storage, as EPRI has shown in some studies and many others have as well, has the potential to increase the overall marginal emissions on the grid if it is not charged and discharged with that in mind. So ideally, all of economically anyway, ideally, all of that would be represented in the markets themselves as they're being resolved so that the market operation was in line with not just the needs of the grid, but the needs of society as well. That's personal opinion. But there are mechanisms like this that could help at least steer things in that direction. If not, a basis by which to do direct controls and out-of-market operations.
Yeah, I would just like to reiterate that you're getting to the crux of many of the challenges here. And it's that price signals when it comes to storage are pretty challenging to quantify, and especially when we don't fully understand what we're tracking yet. So this question, I think, goes along the lines of challenges we are still working on, and I'll add it to my list.
Yeah, I agree. I think having, as you pointed out, having a good transparency of what the emissions are and how it works is the first step. Yeah.
And yeah, maybe just to kind of follow up on that, some really good points. Obviously, this it is challenging to actually. It's impossible, in fact, to actually measure the emissions impact of a given action on the grid that evolves over time, over years, and with many different actors. And so all we can do is look for kind of proxies for that happen in the real world. And so, hourly matching might be one of those. But yeah, we obviously using like a marginal emissions rate to kind of quantify the avoided emissions, this can be useful, but obviously has some issues with it as well, because not all generation is marginal, not all consumers are marginal, and we're working on a system, not on just one plant. So I think it's important to kind of keep those things in mind as well as we think through the impacts of these decisions. But I think, yeah, it's a great question. Maybe one thing on the matching that has kind of come up in other markets at least is the potential ability to integrate these devices into long-term contracting mechanisms. So as corporate customers, for example, look for firmer power purchase agreements, obviously storage should have a role to play in that. We've seen storage in Australia and in the UK signing tolling arrangements to get some sort of long-term visibility on their revenues, given they're capex heavy. And so, yeah, that could be another important kind of revenue stream here that gives more visibility to people investing in storage.
So this next one is specifically for Killian, but I think anyone who wants to speak to it after Killian responds would be great. This is from Jacob asking, how does the EnergyTag standard address trade-offs between time-shifting renewable energy and the potential for increased emissions, especially when storage is operating in a different location and there might be congestion or transmission losses? Are there any restrictions on the market boundaries between the energy storage and the corresponding renewable energy resource that are more granular than a balancing authority or an ISO? And do you see the standard being better suited or best suited to co-located or hybrid storage projects? Number of questions.
I'll try not take up the rest of the time answering. Yeah, well, I kind of was kind of addressing this already. I think what we can see from some of the capacity expansion modeling, without getting too technical now, but we kind of have to get into this question, looking at different power system scenarios that look at the full system effects of different procurement approaches. We do see that this essentially the way that our standard is working and the way storage was modeled and more in those models as well is kind of aligned with our own standards, and we do see positive long run benefits for the system from operating in this way. So in that way, we're aligning with the best available science on this topic that is out there. Again, I think avoiding doing analysis that's purely on a marginal short run basis is important in trying to evaluate the emissions impacts in the long run, which is what matters of these devices, and our standards are definitely trying to align with that and looking at the modeling that's been done on that. In terms of market boundaries, obviously we've seen in the in the clean hydrogen standard drafts out of Treasury, and similarly here in Europe, we've seen more narrower market boundaries than you would typically see in rec markets. We think that's obviously super important to decrease the market boundary and to make the signal more effective. Obviously, given interconnection between ERCOT and the rest of the US, for example, it probably makes sense to try and match the battery charge and discharge with generation and consumption inside an ERCOT, given the vast amount of electricity produced in ERCOT is consumed there. So that is obviously really important to these hourly price signals as well. If you have an hourly signal, but it's happening over very, very broad geographical boundaries, there's too much congestion in between, and the signal gets kind of lost. I kind of agree with your question there, Jacob, as well. We probably should have tighter boundaries, but I think we can only go a step at a time as well. So yeah.
Right. Kind of a twofold question here for everybody. What are, from your different perspectives, what are some learnings and some potential emissions impacts and consequences of the different allocation methodologies? And then maybe more specifically with respect to the storage operator decides method, is there a possibility there for perverse incentive scenario? Curious to hear everyone's reactions and thoughts.
I guess I'll go first since nobody jumped off mute. This is another great question that we are going to be exploring at EPRI in the next several months. We are really curious about not only the emissions impact, so the fact that the same battery system or the same batch of monthly data could show up very differently depending on which allocation method you choose, is a really significant challenge. And then I would also add another question onto that is, how does that hold up in validation and verification? So in the case of the storage operator chooses, there has been discussion amongst those of us who have been thinking a lot about this on how to justify the choices that the storage operator makes. Whereas if you think about another allocation option like first in, first out, there are quantification methods there that will potentially, you can math it, for lack of a better term, and your justification is the math. And the same for the last allocation method, which I don't remember what it's called, but conceptually it is an averaging function where you would take the average emissions intensity and assume that that is dispatched over time, and say you are to charge the battery with additional grid mix or something like that, you would be able to math that emissions intensity as well. There are challenges with every allocation method. This is never going to be perfect. And from my perspective, we can't let the perfect be the enemy of the good. And we have to be able to think about and justify what emissions number we are using for the discharged electricity, and recognize that once an electron enters the grid mix, we can't calculate where it came from. So this is when we have to decouple our thinking on the electricity generation source with the emissions intensity that we are reporting, and just make sure that we are being as accurate as possible.
Yeah, I agree. I think the other thing, one of the points there too, Arin, is we talked about the battery validator, that you sort of have to know what that discharge method is to validate the battery. So I do agree. I think at some point, picking the ones that can be validated with math is really important. So 100% agree, because the registry has to do it, greenhouse gas reporters have to do it. So I think honing in on a few that are auditable and verifiable is the right path as we go forward here.
Yeah, maybe I can just jump in quickly on that. And I think we obviously, given the time, we didn't get a chance to go through them all, but we actually give like a decision matrix. So there's 6 quality criteria that we ask, anyone with using a storage operator decides to go through. Things like auditability, preventing greenwashing, ensuring feasibility and maximizing economics. So there has to be these trade-offs. The reason we have storage operator decides really in the current version of our standard is to leave opportunities open for folks to come back with new methodologies that are tested and that can be justified and audited. Ultimately, storage operator decides will be phased out of any standard, right? Like, of course, we need to come to some agreement on something that's transparent and can be audited, and that people understand how the math works. I think, you know, Arin really could not have put it better. That, you know, we need to find something that people understand, that you can write down in math, and that can be audited, and that's super, super important. But we wanted to kind of leave that opportunity for folks to go out and test methodologies, and maybe there's something we haven't thought about yet. I haven't seen it quite yet, but maybe someone will come up with something that really performs best across those 6 quality criteria.
Great. One more quick and easy one. As storage assets participate and are tracking GCs, you know, in time shifting clean energy, how do you all think about the additionality of these issued granular certificates discharged from storage?
Well, if we're concerned about double counting the carbon benefit or cost of a storage system, you know, I think that would be a concern in some scenarios. You know, the additional a storage system may have already received some implicit or explicit payment financial transaction for that includes the carbon value. You know, maybe it makes its way into market prices somehow. Maybe it does something else and gets in there. So it is a concern, I think. You know, the additionality, if that's the right interpretation of the question. I'm not sure how these folks are addressing it, though.
I can add some perspective here too. We think about storage in the same way that we oftentimes think about transmission and distribution infrastructure from a greenhouse gas emissions accounting perspective. Storage is not a generator. It is holding something, and then it is time shifting it for us. And you can akin time shifting to the movement of electricity on the system. So either think about physical movement or time movement. And so when we think about the accounting for the storage system, in the same way that Killian walked through the charge certificate and the discharge certificate, that would have to be just accounted for once to mitigate double counting. So even though, and this is where we start to, my favorite word seems to be uncouple in this webcast, but this is where we start to uncouple our concepts of electricity flow, the emissions impact, and the financial transaction.
Amazing. Thank you all. So I'll wrap us up here. Well timed, everybody. Thanks to all our speakers and all the participants for today's webinar. Before we log off, I'd like to issue a quick call to action for everyone who's still sticking around. We hope a lot of you on this call are exploring storage projects. And if you're interested or curious about doing demonstrations using the EnergyTag standards on real life assets, we would love to be in touch. We're hoping to see a lot more examples like the one Quinbrook discussed today. And I know a lot of folks are already actively involved there. The EnergyTag standard, also not in stone. It is a living, breathing product. And there's, as talked about today, a lot of areas where we're hoping to get further input and make improvements. So we hope you all keep your ears out for the next round of stakeholder engagements, and so that the next iteration of this is broadly applicable, accurate, and feasible. Thank you all for attending, and hope you have a great day.
Thanks, everyone.
Thanks, guys.
Thanks, everybody.
Bye.
Bye.